The universe exists external to our minds and exists whether or not we observe or measure it. Like you, me, and Einstein would like to think that the moon exists whether or not we are looking at it. So, keeping in mind that we live in a local realism, let's have a thought experiment. This thought experiment involves two friends separated at a great distance that they cannot communicate in any way, and each of them has access to one half of an entangled 2-qubit pair. Qubit works here as a coin to return the value either 0 or 1. In the game, there are two cooperating players, Alain, Bob, and a referee, Charlie. We will call them A, B, and C respectively. At the start of the game, Charlie chooses bit X and Y from 0 or 1 randomly. X is sent to Alice and Y is sent to Bob as inputs. Alice and Bob must then each respond to Charlie with bits A, B respectively from 0 or 1. Now once Alice and Bob send their responses back to Charlie, Charlie tests a condition that if X is equal to Y is equal to 1, then A does not equal to B, else A is equal to B for all other input combinations. If this equality holds, then Alice and Bob win, and if not, then they lose. It also required that Alice and Bob's responses can only depend on bits they see. So Alice's response A depends only on X, and similarly for Bob. This means that Alice and Bob are forbidden from directly communicating with each other about the values of the bits sent to them by Charlie. Alice and Bob applied a classical strategy to get the most results, which led them to win. So before the game starts, both of the players calculate the possible combinations of inputs they can get versus the output. After some time they realized that out of all possible strategies, they can achieve the highest winning probability of 3/4, which is 75%, without communicating with each other, only when they answer 0. Therefore, they programmed their qubits in such a way that it gives output 0 each time they receive the input from Charlie. The strategy worked well and they ended up winning nearly 3/4 time of every time they played the game. Intuitively, the given strategy is the best possible way you and I would have advised in a local realism. We overlooked one inevitable factor, which is quantum correlation due to entanglement. Practically, we can program our qubits using correlation principle in such a way that we can achieve a winning probability of up to 85%. We have created a computer simulation to mimic a result. This is a code for the classical method when we did not take correlation into consideration. After running the simulation, we get the winning probability of 75%. Let us change our code and apply quantum correlation. Then we can see the results winning probability up to 85%. This results mean that our seemingly reasonable assumption that we started with local realism above is invalid. This is easily explained by quantum mechanics, and therefore we must conclude that the moon is not there when we are looking at it.